Alright, this is going to be our second review of some of our practice problems for our upcoming air test. This review, the first one kind of talked about a lot of the transformations. This one's going to talk about some of our proofs. We did proofs first semester of the year, so this will be a good thing to kind of review, kind of see what's going on. So what the problem says, it says, place the statements and reasons in the table to complete the proof that shows parallelogram PQRS is a rhombus. So we know it's a parallelogram. We want to show it's a rhombus. So basically this is the body of our proof, and these are the possible reasons. So on the test, what you do is you would select one and you drag and drop it into the correct box to show that's the answer you want to pick. So you'll basically complete the proof on the table up here. So the first thing I would do is with any of these is I would go ahead and see what information they give us. They tell us some ordered pairs for 3 of the vertices. So it says Q is 8, 5. So I'm just going to draw a little picture down here. It says Q is 8, 5. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So that's going to be right there. So Q is 8, 5. It tells us R is 5, 1. So R is going to be 5 and up 1. 1, 2, 3, 4, 5, up 1. So there's R at 5, 1. And it says S is at 2, 5. So over 2, up 1, 2, 3, 4, 5. So there's there. Okay. There's S. Now what it doesn't tell us, we know we have parallelogram PQRS. Well, we have R, Q, and S, but we don't have P. So P is going to be somewhere up here. I don't really know where it is, and I don't think I really will need to know where it is. But I have this parallelogram. So I want to prove that basically this is a rhombus. Now what I know is I know in a parallelogram we have opposite sides are parallel and opposite sides are the same. So we know these opposite sides are the same. The goal in a rhombus is I just want to try to prove that all 4 sides are the same. So the nice thing here is since we have ordered pairs, we can actually figure out what the distance is between them. We have our distance formula, which we've used quite a few times in the first review. The distance equation, remember, is x1 minus x2 squared plus y1 minus y2 squared. So if I maybe find it says Pythagorean Theorem. Pythagorean Theorem, anytime you see this, this is just another thing for distance formula. Because if you remember, the distance formula was actually a part of the Pythagorean Theorem. So if I find the distance of, say, QR, then I can use square root 8 minus 5 squared plus 5 minus 1 squared. So the distance between those would be 3 squared plus 4 squared. So 3 squared plus 4 squared is 25. So this is the square root of 25. So that is 5. So right away I know QR is 5. I know this side is 5. So that is one of the things I have. QR is 5. So I'm going to put that as my first reason. And again, you just have to recognize that when it says Pythagorean Theorem, that's really talking about distance. Because the distance formula is an example of Pythagorean Theorem. Okay, so now I'm going to try to find the distance in our other ones. I'm going to try to find the difference between SR. So we have 2, 5 and 5, 1. So if I find the distance between those, so it's 2 minus 5 squared plus 5 minus 1 squared. So that's going to be negative 3 squared plus 4 squared. Well, that's going to turn out to be the same thing. That's 9 plus 16, so that's square root of 25, so that's also 5. So SR in our problem is also 5. So that's this reason here. So I'll put that up there. And the reason we know SR is 5, that's because of the distance formula, but that's not one of our reasons. So like we said, we'll use the Pythagorean theorem as our reason, because it's the same thing. Okay, so now what it says is it says SR is equal to QR substitution, because they're both equal to 5, so we know these are now equal. So this one is equal to this one. So we knew the opposites were the same, but now we know these two next to each other are the same. So SR is congruent to QR because they are both the same length. And that's the definition of being congruent. The next statement says PS is congruent to QR. And we already knew that because these were opposite sides in a parallelogram. So now the only thing we have left is we can also say that Q or SP, which is this guy up here, we know SP is also congruent to QR or RQ. And that would be so we're just saying that SR is the same as congruent to PQ. And that's again because opposite sides of a parallelogram, so we could just say property of a parallelogram. Because we know in a parallelogram, opposite sides are congruent. So now we've proved all four sides are the same. And in a rhombus, it's a parallelogram that has all four sides the same. So we've proved what we had. So we proved that these two bottom ones were 5. And then we know since opposite ones are the same, this is 5, and now they're all the same. Okay, so that was definitely our hardest proof. So let's look at a little easier one. So this one says, given triangle ABC is isosceles, that means that the two of the sides are the same and one is not. And point D is the midpoint of AC, so D is in the middle of AC. Prove that angle BAC is congruent to BCA. So the first statement says triangle ABC is isosceles and D is the midpoint. That's of course given. Okay, those are given statements. So then it says AD, which is this guy down here, will be congruent to DC. So if I zoom in on the picture, it's saying AD is the same as DC, but that's kind of obvious because D is the midpoint. If D is the midpoint, then the two parts it breaks it into have to be equal. Then it says BA is congruent to BC, which is already said, because we said it's an isosceles triangle, so this side is congruent to this side. That was already given to us. Then an interesting one says BD exists. So if I draw BD, BD is this segment. And it exists because I can connect basically any 2 points. So that is a thing. And what you'll see is this breaks us now into two triangles. So now we have to start giving some reasons. It says BD is congruent to BD. Why is BD the same length as itself? Well, if I look at my reasons, we had this one earlier in the year. The one that shows that something is the same as itself is our reflexive property. Reflexive means AB is the same as AB, or in this case, BD is the same as BD. So that is the reflexive property. So now it says triangle ABD is congruent to triangle CBD. Let's see why that's true. So it's saying this triangle on the left is congruent to this triangle on the right. Well, we know these two, they both have two sides in common, but then we said that this side was congruent to itself. So we have three sides the same in each triangle. So the reason these two triangles are congruent would just simply be side, side, side. And now we know that these two triangles are exactly the same. Then we know all their sides and angles are the same. So I can say these two angles are the same. And the reason we said that is our CPCTC, which is our corresponding parts of congruent triangles are congruent. So if we have two triangles that are the exact same, it means all the angles and all the sides are also congruent. Okay, so let's look at this next one. This is a nicer one because you only have to find one reason. It says, what's the missing reason in this partial proof? So this proof shows that opposite angles of parallelograms are congruent. So we're given that ABCD is a parallelogram with diagonal AC. So I'm just going to start working through the proof and see why these are true. So it says this is a parallelogram with a diagonal. Yeah, that was given. AB is parallel to CD, and BC is parallel to AD because these are the sides, right? So we can use our little arrow notation to say these are both parallel if we'd like. So then it's saying angle 1 and angle 4 are the same, and angle 2 and angle 3 are the same. And that's just because of our alternate interior angles, because we have these parallel lines cut by this other line. So we have these congruent angles. So then here's where the proof gets interesting. So it says angle 2, measure of angle 2, is equal to measure of angle 3, and measure of angle 1 is equal to the measure of angle 4. And that's just basically because if the angles are congruent, they're the same measure. Now what we know is we know that angle 1 plus angle 2 must equal angle 4 plus angle 2. Now here's why. Because I know these two are the same, if I just add angle 2 to both of them, they still must be the same. So if I add just the same thing to both sides, it has to still be the same. These are still equal. So here's the big thing. So we're at this line. So now somehow we replace this measure of angle 2. Everything else in the next line is the same. It says measure of angle 1 plus measure of angle 2 equals measure of angle 4. But now it says plus measure of angle 3. So we've replaced 2 with 3, which we knew is true from up here. So which reason would make that true? So let's look at our choices. Angle side angle, that makes no sense. That's dealing with congruent triangles. Substitution. Did we substitute something in? We did, so that is going to be our answer. Because we put 3 in for 2, and we knew those were the same. It's not angle addition. It's not two angles added together. And alternate interior angles, that's true, but that's not what we're dealing with in this case. So in this case, it's a simple substitution. I'm substituting angle 2 for angle 3 in this case. Alright, so let's look at our last one. Triangle PQR is shown here, where ST is parallel to RQ, and Marta wants to prove SR over PS equals TQ over PT. So let's see what we have. So we start off by saying these are parallel, that's fine. And then we're saying angle PST, which is this angle here, just highlight a little bit, PST is the same as angle R. And that is because these are corresponding angles. Because remember, ST and RQ are parallel, so if I were to continue them, they're parallel. And we have this other line that cuts the two parallel lines. What we also know is PTS, which is this guy, is the same as angle Q. That's fine. So what it's trying to say now is triangle PQR, which is the whole triangle. PQR is the whole thing. So here's, I'm just going to try to draw it here to the side. So PQR, this whole thing, and then it's talking about triangle PTS, which is the little guy up here, PTS. But what I know is I know this one, this Q is the same as this one, and I know this S is the same as this one. Oops. Only one mark on those, because these are the same. So it's saying, why are these two triangles similar? Not congruent, why are they similar? Well, the biggest reason we ever had when things are similar, that would be AA. If you have two angles the same, and here's our reasons down here, two angles being the same, then we know that they are similar. And since we have two angles the exact same, then those are similar. Now what we can say now that we know they're similar, we can say lots of things. But what we're trying to get at is we're trying to get at the sides being proportional. So I could say really anything is proportional here. So if I start looking at proportional statements, PR would be proportional to PS. So I could write PR over PS is the same as, I could pick a different one of the big ones. So I could say PQ is proportional to PT. And then I could also say that RQ, which is the bottom, is proportional to ST. So all these are the same. All these are true. So if I look down at my reasons, I don't see a lot of those. But what I do see is I see this one right here, PR over PS equals PQ over PT. That's our first part. So that's the reason I would put there. So let me make it a little bigger. So this is PR over PS. And again, I just used my two similar triangles and wrote all the ratios. And then since this is kind of a test where you can see what the reason they want you to put there, I'll just put those two. And the reason that's true, why can we do proportions in similar triangles? Well, that's because corresponding parts of similar triangles are proportional. So that would be this reason here. So corresponding parts, I'm not going to write it, corresponding parts of similar triangles are proportional. So if you have two similar triangles, you can divide all their sides and get the same ratio every time.